Okay, so now what happens? So this was one charge moving, right? An isolated charge moving by itself in a B field, in a magnetic field. Now, what happens when a collection of charges are somehow contained? So what do we call a collection of charges moving? Current. So a collection of charges that move through something is called current. In intro 1, we only talked about the current that's flowing through a wire. Now that we are in a big people class, we are going to additionally talk about what happens to that current when it flows over a surface and when it flows over a 3D region. The physics of it doesn't change. It's just that we need to introduce a few new ideas to compensate for that. Do you remember when we were doing electrostatics, we went from a linear charge density to a surface charge density to a volume charge density? It's going to be almost identical to that. We're going to go from linear to volume to surface to volume. Are we ready? Okay, step number 1. We are going to talk about the easiest one, which we have also seen in intro, but we're going to expand on that a little bit. So a wire, a current flowing through a wire. And let's say that this current is upwards. As a result of this current, magnetic field will be set up. Can you guys tell me the direction of the magnetic field? It is, again, the right-hand rule. Remember, it's what direction. So look at this. This was V flowing. So I'm looking at this. V flowing, B in certain way, and gives me the resulting force, right? So in this case, the easiest way to think about it is hold a pencil, wrap your fingers around it. That will be the direction of the magnetic field. So the magnetic field will actually curl around your finger. So it will go, it's going to go like this, right? So it will go in and out. Goes in and then it comes out of the paper. So if you're holding a sheet of paper, it goes into and then comes out. And what's the formula that we learned in intro? F was I L cross B, where L is the length, I is the current, and B is the field. It's the same, almost the same thing. If you look at them side by side, do you see the similarities? That's why I wanted you to see them on one paper, because we always see them in different chapters and we never make that connection necessarily, unless you see them one-on-one and you're like, oh, it's not different. It's just that in one case we have one charge and in one case we have a bunch of charges that are just moving together. And then because they're confined to a length, I won't have a velocity, but I'll just have a dl. And think about it. What is this I? It's just dq over dt, right? Times L times B. So if I move this together, what is that? Nothing other than B. Do you see it? Magic. So it's not a new formula you have to learn. It's just the same formula being applied to something new. Woohoo! Again, we didn't do anything new. Isn't that exciting? Sorry, I'm going to erase that. That was, right? Make sense? Okay. Now, Griffith does a little bit more beyond this. What he says is, instead of talking about, so this is what Griffiths does, which is amazing. So he says, instead of talking about just I equals dq over dt, he defines current as lambda v. Lambda is now my line charge. Traveling down a wire at speed v. Also note, this definition makes your current a vector. However, in general, we ignore the fact that current is a vector because we've already given it a direction, right? Okay, then he also says, what is that wire segment? So suppose this is your wire segment that you are worried about, and the length of the wire segment, say it's DL. So then he says, I can define my length, segment length, as, oh, I want to make sure that I don't mess up too much on my surface. Segment length as speed times delta t. Am I allowed to do that? Speed equals dl over dt. So may I define my delta L as v delta t? And if I define my current as dq over dt, may I also say I dt equals dq? Or may I say lambda v dt equals dq? Because of my definition up here of current. Then does this segment, delta D, delta L, carries current and if it is a steady current, may I replace this Q with delta V dt? Note, I have just gotten rid of the delta L in my equation. So all I'm concerned about basically is the Q that's flowing through that segment in time t, which is a basic definition of current.